Welcome to our video covering related rates. This is an application of differentiation, specifically implicit differentiation, because the variables really matter here. We are going to be finding different equations, usually geometric, and related rates problems are simply a method of problem solving, and it allows us to see how different variables change with respect to time. We will start by finding some related rates equations. In number 1, we can see that this is the distance formula between any 2 points, in this case called x and y. We want to differentiate this equation with respect to time in order to find dt, the derivative of d, distance, with respect to time. So we want to take the derivative of each side of this equation with respect to time. So the left is literally the derivative of d with respect to time. Then we'll put equals. Now this is really, if you want to rewrite it up here, x squared plus y squared raised to the 1/2. So we'll be using the power rule and the chain rule. So I'm going to bring that 1/2 out front. Then we keep the inside the same. Then using the power rule still, we'll raise to the negative 1/2. Then we invoke the chain rule and take the derivative of our inside function with respect to time. The derivative of x squared with respect to time is 2x times dx dt, using the chain rule, plus, in a similar way, 2y times dy dt. Cleaning this up a little bit more, if you'd like, the 1/2 will go out front still, and this is actually going to be a fraction. In our denominator is the square root of x squared plus y squared. And in the numerator, I'll erase the 1 since it's implied, and we have 2. I'll factor that 2 out from this term over here. We're left with x dx dt plus y dy dt, and I factored that 2 out because the 2's can ultimately cancel. So dd dt is this right here. The next 2 examples involve volume. If we take a look at number 2, this is actually the volume of a sphere formula. And we want, again, to differentiate with respect to time, t. So we will find dv dt by doing that. If we differentiate with respect to time for v, we get dv dt, which is what we want. Then on the right-hand side, we again need to differentiate with respect to time. 4/3 pi is just a constant out front. Remember, pi is just, or coefficient rather, because it's attached to the r cubed. So 4/3 pi is our coefficient. We're basically just differentiating this r cubed with respect to time. Using the power rule, we'll bring the 3 out front. 3 times that 4/3 pi ends up just being 4 pi. And then the power rule will raise it now to the second power. Using the chain rule, we have to multiply by the derivative of our inside function r with respect to time, which is dr dt. Again, we need to do this because what we're differentiating with respect to, t or time, is not this same variable here. That is the implicit differentiation part of this. So we have found dv dt by differentiating both sides of our volume formula for a sphere with respect to time. Problem 3 is again a volume formula, and we want to find the dv dt, the derivative of volume with respect to time, but in this case this is the volume of a cone. It involves not just the radius like a sphere did, but radius and also height, 2 variables. Note that these 2 variables are being multiplied. We will need to use the product rule in here. So in order to differentiate it with respect to time, we'll do that with v, it's dv dt. That's a pretty easy part. Then the equals part are pi over 3, I will keep out front, and then do the product rule inside here. I'm not using pi over 3 as part of the product, just because it's simpler to keep it out front. So we have r squared times h. We can think about this as a u and a v if we'd like. So off to the side, if you prefer to write that out, our u would be r squared and our v would be h du, or u prime. You can write it either way. U prime with respect to t would be 2r dr dt, and v prime, or dv dt, would be the derivative of h with respect to time, which is just 1 times dh dt. All right, so once we found that, we'll do our product rule, which will be u times v prime, which is r squared times dh dt, plus vu prime, which is h times 2r dr dt. Cleaning this up a little bit, I like to keep the pi thirds out in front, but it's up to you if you'd like to distribute it through. I'll leave this first term as r squared dh dt, and our second term, we'll put the 2 out in front, so it'll be 2rh dr dt. So note that number 3 is probably the most complex. Well, number 1 was pretty complex too, basically because we had 2 variables inside our equation or our formula to start. And so we ended up having, like in number 1, dx dt and dy dt in the final derived equation. Same with this dv dt. We started with an r and an h, as opposed to in problem 2 where we just had 1. So we do at times need to still use those same derivative rules, such as the product rule, if our equation calls for it. Now these are the steps to solve a related rates word problem, which we will see 3 examples of here in just a moment. I will go back through this more in depth once we've actually done a problem, but the first 2 steps are what you'd think. We want to understand the problem, write out what we're given and what we know, and what are we asked to find, most importantly. The second step is to draw it out, make a mathematical model, and this is something we'll talk about that's important. We want to distinguish a constant from a rate of change. A constant is something that stays constant or stays consistent as a numerical value throughout the entire problem. It never changes. Then a rate of change, we might actually be given a number, but it might say at that exact moment or at that instant. That is not a constant. Even all numbers in these problems are not constant, so we're going to differentiate between the 2. Then we want to write out the appropriate equation. It's usually geometric. It might be the Pythagorean theorem or the volume of a cone. Then we want to differentiate with respect to time. If you did not look at those first 3 examples that we just did, I recommend doing that. We differentiated with respect to time. Then finally, after differentiating, we can substitute back with those instantaneous values that we got, those things that were not constants but were still numerical values. At the very end, we want to do what seems obvious, but a lot of times we might get a mathematical answer that might not be answering the exact question that was asked. So we want to make sure that we answer the question that was being asked. Let's use this process to solve our first related rates problem, and we'll make sure that we've gone through the process properly, then we'll revisit it. In example 1, we have a hot air balloon. It's rising straight up from a level field, and it's tracked by a rangefinder that's 500 feet from the liftoff point. At the moment the rangefinder's elevation angle is pi over 4, this angle is increasing at the rate of 0.14 radians per minute. How fast is the balloon rising at that moment? Well, the first thing we want to do is write out anything that we know. It looks like we have this constant here, and instead of writing it out, I'm just going to underline. So this is a constant. The rangefinder is 500 feet from the liftoff point. The hot air balloon is rising straight up. That'll help us with drawing. Then it says, at the moment, the rangefinder's elevation is pi over 4. Now, note that both 500 and an elevation angle being pi over 4, those are both numerical values. However, this one is a constant. This rangefinder's not moving. This is a constant that's consistent throughout our problem. This angle being pi over 4 is not. It's saying at that exact moment. So this would not be a constant that we would label. Then we see the angle is increasing, so that is a rate of change. Angle is increasing, radians per minute, and we're asked to find how fast is the balloon rising at that moment. So in green, I'm going to underline what we're asked to find. All right, I haven't written down too much yet, but I did underline a few important things. The second thing that we want to do is just draw. So let's draw this out. We know that we have a hot air balloon rising straight up from a field. So my hot air balloon, which my drawing of this will be, we'll see. There's my hot air balloon. And something that's changing is the height of this hot air balloon. So I'm going to call that H. Then we have it on a level field, so we know that this is perpendicular if it's rising straight up, so that's a couple things that I know so far. Then we know that there's a range finder. It's 500 feet from the liftoff point. That is not something that I know how to draw, so I'm just going to call it range finder. And I know that the distance between the liftoff point, which is right here, and the range finder is 500 feet, and that doesn't ever change. So I'll call that 500. Then we're also talking about an angle. I don't want to actually write in pi over 4 or 0.14 because that's talking at an exact moment. And so those are not constants like the 500 is. Instead, I'm going to use variables because those are things that are changing. Now, it looks like the angle, the moment the rangefinder's elevation angle is pi over 4. So an elevation angle means from the ground up. So I'm going to draw this right here, and we've made a right triangle. And inside, this is the angle that changes. So I'm going to label it with a theta there, which is how we normally talk about angles. So basically, we need to kind of write out the couple things that we know off to the side. We know something about a specific moment. So I'm going to write at the moment, right down here, ATM. We know at the moment the rangefinder's elevation is pi over 4, so we know that when the angle is pi over 4, we know the angle is increasing at a certain rate. We write that as d theta dt, the way the angle is changing with respect to time, and it's 0.14 radians per minute. So we have successfully drawn this out and written out things that we're looking for. Actually, the very last thing I do want to do is write this, like what we're being asked, write that out in mathematical language. How fast is the balloon rising at that moment? That's asking us, how is the height changing? So the height's change over time is written as dh dt. We want to know what is that at the moment, at this moment here. That's essentially what we're looking for. So we need an overall equation so that once we take the derivative with respect to time of that equation, we can plug in the stuff that we know and answer the question being asked. Let's figure out what that equation should be. It needs to relate 500, h, and theta. Why does it need to relate those things? Because that's the stuff that we got. So let's think about what geometric equation can relate those things. Well, we have a right triangle, so the first thing that comes to my mind may be the Pythagorean theorem. But the Pythagorean theorem doesn't have to do with angles specifically. It just has to do with the side lengths of the three sides of the right triangle. So that's out of the question. What has to do with the angles and two side lengths is SOHCAHTOA, sine, cosine, and tangent. That's the only other real option that we can have for a right triangle. So we see this angle here, theta, is the one in question, and we know information about the opposite and the adjacent. Therefore, we're going to use tangent. So I'm just going to write out what I know. I know that the tangent of theta equals the height over 500 because tangent is opposite over adjacent. Now from here, since you have your equation, you could just start differentiating with respect to time. Or, since we can look into the future of what we need dh dt, you could totally solve for h here at that point, which is what I'm actually going to do. So I'm going to multiply both sides by 500 and write h on the left-hand side. So h equals 500 tan theta. Again, did not have to rearrange it like that, but I like having like the thing that I want to solve for on the left by itself. So now at this point, I'm going to differentiate with respect to time. I'll do that in pink here. So I'm going to differentiate both sides of this equation with respect to time. This is simply saying I'm about to differentiate with respect to t. So I'm going to do that for h, and I'll get dh dt equals 500. Then what is the derivative of tangent of theta? It is secant squared theta times the derivative of theta with respect to t, which is d theta dt. So we have now found our calculus equation that we can now plug in the at the moment constants into, the at the moment values. So we couldn't plug these in too early because they would freeze our equation and they wouldn't allow us to actually differentiate. Like if we plugged in pi over 4 here, that is just a value, the tangent of pi over 4. It wouldn't allow us to have done the calculus of differentiating. So now we can plug in our pi over 4 and 0.14. And then once we plug those two things in, we'll get what dh dt is. So dh dt equals 500 times secant squared of pi over 4, so plugging in what we know, times 0.14. We know that secant is just the reciprocal of cosine, and I know that the cosine of pi over 4 is root 2 over 2. So I'm going to flip that over, and I know that the secant of pi over 4 would be 2 over root 2, and then that gets squared, then multiplied by 0.14. From this point, you can use your calculator. I mean, I guess you could have done it from the start, but I'm going to see what I end up getting here. I know that when I square this, I'll get 4 over 2, which is just 2. So we really have 1,000 times 0.14, which is just 140 when you move the decimal point over 3 times. Now, we want to make sure that we are like answering the question and labeling properly. So it's asking us how fast is the balloon rising at that moment, which is dh dt. It's how the height's changing over time. So it's how fast the balloon's rising. It's a positive number. That means it actually is rising. And let's figure out what our labels or our units would be for that. Something is rising like with respect to time. So let's see if we know it's per minute in this case, and we also know it's feet. It wouldn't make sense to be rising at radians per minute since that's how the angle changes. So since this is in feet and minutes, those are the proper units to use for how fast the balloon is rising. So here is our final answer. Revisiting this page, did we understand the balloon problem? Yes, we read through it, figured out what we knew and what we were being asked to find, dh dt. We drew it out, kind of 1 and 2 went together. We definitely distinguished the constant of 500, which didn't change ever, from the rates of change, how the angle was changing at that exact time. So we saw that we couldn't plug those in at the start because those were actually variables. We only knew something at that one moment. Then we wrote out the appropriate equation. We had to sort of rack our brain a little bit, and it ended up being a tangent equals opposite over adjacent. It was geometry. Then we differentiated that tangent equation, h equals 500 tan theta. We differentiated with respect to time. Then finally, after we did our calculus, we could plug back in those two like at the moment quantities that we were given from the start, and then we made sure that we answered the question and had our proper units. I'm actually going to add that at the very end, so make sure it's in proper units. So answer the question with proper units. We had to look back at the question to make sure our units made sense, and it was feet per minute since it was a rate of change. In example number 2, we have a police cruiser approaching a right-angled intersection from the north, chasing a speeding car that has turned the corner at the intersection and is now moving due east. We are given some information about a specific moment in time here next. It says when the cruiser is 0.6 miles north of the intersection and the speeding car is 0.8 miles east. The cops determine with radar that the distance between them and that speeding car is increasing at 20 miles per hour. If the cruiser is moving at 60 miles per hour at that instant, once again, we're asked to find the speed of the speeding car. All right, there's a lot going on here. The first thing I'm going to do is simply draw a picture. I know that's number 2, but a lot of times numbers 1 and 2 kind of go together. They help us figure out our variables and what we're asked to find and how to label that. So let's draw an intersection, and it's a right-angled intersection, and we only care about the north and the east. So instead of drawing all 4 ways on the intersection, I'm just going to draw north and east, and then I know we have a right angle here. Then I want to figure out where the police cruiser is. So I'm going to draw a police cruiser in pink. I guess that's the most police kind of color I have right now. And there's my turtle-like car. So there's a car, and that's the police car. Then the speeding car has gone this way and then turned this way, east. So our speeding car, I'll put in yellow, and the speeding car is over here. This is an interesting problem because we are not really given anything that's constant the whole time. If you think about the situation, this police cruiser is moving, technically it's moving south, and then the speeding car is moving east. Nothing's remaining constant in this entire problem. It's constantly changing and moving, but we do have all this information at a specific moment. The very last thing that we need to do is realize that there's another sort of like lurking variable in here, and it says that the distance between them, the police, and the speeding car is increasing at 20 miles per hour. The distance between them would be this hypotenuse right here. And I say hypotenuse because we're dealing with a right triangle. So I'm going to call that length between them, that distance between them, d. And I'm going to have a capital D because all the d, whatever dt, is all lowercase. So that's a distance between them. The way that the police is moving is this way, moving south. So I'm going to call that P. And I'm going to call the speeding car moving this way S for speeding car. You can call this whatever you want. A lot of times your book uses like X, Y, and Z, but I like using variables that help me know what I'm actually talking about. Now let's figure out what we're being asked to find. We're being asked to find the speed of the speeding car at that exact moment. So that would be ds dt. So we're asked to find ds dt at a moment when we know a bunch of stuff. At a moment when we know the cruiser is 0.6 miles north of the intersection. So we know P, that distance, is 0.6. We also know that the speeding car is 0.8 miles to the east, so we know S, that distance, is 0.8. Then we also know some rates of change. We know that the distance between them and the speeding car is increasing at 20 miles per hour, so that would be dd dt is 20, and it's increasing, so it's going to be positive. Then an interesting idea is we know the cruiser is moving at 60 miles per hour. The cruiser is moving down towards the intersection, so its distance to the intersection is decreasing. Therefore, we are going to call dp dt negative 60 because its distance to the point that we care about, the intersection, is decreasing. Now that we have set up our problem, figured out what we're looking for, drawn it all out, labeled it, and got all these values here that we'll eventually plug in after differentiating, we now need to figure out the equation or formula that goes with this problem. Well, again, we have a right triangle, but we don't care about angles at all. We do have a relationship between all three sides. Therefore, we're going to be using the Pythagorean theorem. The Pythagorean theorem tells us that a squared plus b squared equals c squared, where a and b are the legs and c is the hypotenuse. So our two legs are p and s, so it'll be p squared plus s squared equals d squared. Then we can take the derivative with respect to time for each one of these, both sides of the equation. The derivative with respect to time of p squared is 2p dp dt. The derivative of s squared with respect to time is 2s times ds dt. And similarly, the derivative with d squared with respect to time is 2d dd dt. Now from here, I want to note how many variables we have to plug in and what we're looking for. We have p, dp dt, s, ds dt, and d dt. We have 6 different variables. So that means we need to plug in 5 of them to solve for ds dt. This is what we want to solve for. Do we know p? Yep. Do we know dp dt? Yeah. How about s? Yes. This is what we're looking for. Do we know d? No. But do we know dd dt? Yes. We need to find out what d is at this exact moment. Well, if p is 0.6 and s is 0.8, can we use the Pythagorean theorem to find d? We totally can. 0.6 squared plus 0.8 squared would equal d squared. D ends up being 1. So we also know that information. So let's plug in what we know and solve for ds dt. I have plugged in everything and we're looking for ds dt now, so we can solve. Solving for ds dt gives us 70. We do want to make sure that we're answering the question. The question is, what is the speed of the speeding car? Well, the speeds here are given in miles per hour, so that makes sense for this. So it'll be miles per hour, which we obviously abbreviate as mph. One special part of this problem was the fact that we made dp dt negative, where d dt was positive, and ds dt ended up also being positive. Let's talk about why dp dt is negative in a little bit more depth. If you look at our drawing, we see that p, d, and s are all lengths or distances. The reason I have an arrow is because this is dp dt, it shows the movement, but p is a length or a distance, and so is s, and so is d. Now if we look at d, that ended up being 1 unit, and how it changed was positive, 20 miles per hour. The reason that it's positive is because the problem told us it was. It said that the distance between both of them is increasing at 20 miles per hour. That means it's positive. However, the reason we made dp dt negative is because of how this distance p is changing. Right here, that's what that means. It was becoming shorter. That's because this distance here, this cop car, was driving south, and therefore the distance p was decreasing. Because the distance p was decreasing, its rate of change had to be negative. So that is why we knew to make dd dt positive, because this distance was increasing, where dp dt was made negative because the distance p was decreasing. It also makes sense that ds dt is positive because this car is traveling away from the intersection, and this length s ends up getting longer or increasing. This last example is about a conical tank, which just is an adjective for cone. So we have water running into this conical tank at a rate of 9 cubic feet per minute. That is volume because it's cubic. The tank stands point down, and it has a height of 10 feet and a base radius of 4 feet. We want to know how fast is the water level rising when the water is 6 feet deep. It's an interesting concept because when we have this conical tank, which looks just like this here, and water's coming into it, it fills up very quickly. Like the rate of change of the height would be very fast at the beginning because there's not like that much space for it. So it rises very quickly. However, once it starts to like spread out more, and the water will come in and spread out horizontally rather than vertically, the rate of change of the height of the water is going to start decreasing. So it's an interesting idea. We have water coming into the tank at a constant rate of change here, 9 cubic feet per minute, because the water coming in might be from a hose or something, and that rate's not going to change. But the rate of change of the height of the water will change. So let's write out what we know. We drew out the cone. We know that dv dt, the rate of change of the volume with respect to time, is 9 cubic feet per minute. We also know two constants here, and they're constants. They're never going to change because they're describing the tank, and the tank is not like changing shape or anything. What's changing is the water inside the tank, which is the volume. So we have the height of the tank is 10 feet, and we have the radius here, which is 4. So that remains constant. What doesn't remain constant is the height and the radius of the water inside. So I'll draw that. But what we can see is happening here is there's going to be similar triangles. We see that these similar triangles come into play right here. So this 10 and 4 are the constant relationship between these two side lengths here, the height and the radius of the circle, in this case the base of the right triangle. And then we have the height and the radius of the water inside the conical tank as well, and they're going to have the same proportions to 10 to 4 or 4 to 10, however we want to look at that. And that's important because that provides us with a relationship between these two variables. Then the other thing that we want to do is figure out what we're asked to find. We are asked to find the rate of change of the height of the water. So the height of the water we've already labeled as h. I just labeled it over here instead of in here, but same idea. So h, so we're looking for dh dt, how the height's changing, when the height of the water is 6 feet. So when h is 6. Now, because of the relationship between r and h, we also know what the radius would be at this point, just because it's a proportion. So 10 to 4 equals 6 to r, and we could find r. But let's see if we actually need that or not. There's two ways to solve this problem overall, and this is basically the setup for both of those ways. We know that regardless of the way that we choose, we do need to set up our equation. Our equation is going to be the volume of a cone, which is 1/3 pi, or pi over 3, r squared h. Now we can see that when we do find dv dt, meaning when we differentiate both sides with respect to t, we're going to have to use the product rule here, and we're going to have a dr dt and a dh dt to deal with. And we'll also have an r and an h. Well, that is all good, except we don't know what dr dt is. If we look over here, we know dv dt, we know h, and we also said we could find r quickly, and we are looking to solve for dh dt, but we don't have any information about dr dt. So we kind of run into a wall there. Now, what we could do to get around that is we can actually just turn this into an equation that is only in terms of h rather than in terms of r and h, and we can do that using substitution. Let's try to figure out what r is in terms of h so we can get v solely in terms of h and not have to worry about r. Doing that, we'll set up a proportion. So what we know is the relationship between r and h is that r over h is 4 to 10, which is 2 to 5. I'll just simplify it for simplicity. And then in order to solve for r, so we can replace it or substitute it into our volume equation up there, so I'm going to multiply both sides of this equation by h, so we'll have r equals 2/5 h, or 2h over 5. So we now can successfully plug that in for r up there, so we do not have to deal with r or dr dt at all in this problem, and that is part of one way of solving this related rates problem. So doing this, we can find the equation for volume and simply replace r with 2h over 5, square it, and then again multiply by h. When we do this, we'll have 4h squared over 25, and then times h again. And cleaning this up, we'll have 4 pi over 75, and then we have h cubed. I wrote h cubed off to the side instead of in the numerator to kind of show the difference between the coefficient out front and just the variable. So now we have volume solely in terms of h, and differentiating with respect to t will be a lot simpler. So differentiating with respect to t, we'll have dv dt equals, we'll bring the 3 out front. The 3 cancels with the 75 when we are taking the derivative, so we'll have 4 pi over 25 h squared, and then using the chain rule, we'll have times dh dt. Now this is great because we got rid of r, so we don't really care about r at all. We know dv dt is 9 at this specific moment, or actually always. And we also are looking to look for dh dt, and we know h is 6. So we don't have anything like that will be left over in terms of a variable to plug in. So dv dt will be 9. We'll plug in 6 for h, so we'll get 36 here. And then we're looking for dh dt. So we'll have 9 equals 4 times 36 is 144. So it's 144 pi over 25 times dh dt. Now I want to get rid of this 144 pi over 25. So I'm going to multiply both sides by that reciprocal. So 25 over 144 pi. And when we multiply this side by that, that'll go away. So that cancels. When we multiply over here on this left-hand side, 9 and 144 are both divisible by 9. So being both divisible by 9, we'll end up getting 16 and 1. So we're left with 25 over 16 pi equals dh dt. Depending on the problem, sometimes we can leave it like this, especially if it's AP calculus and you're looking to just do things by hand, or you can put this in your calculator. So we can also say that this would be 0.497, and then we do need units, so it's either 25 over 16 pi or 0.497, and it's the rate of change of the height with respect to time. So let's look back, and our units are in feet. So it would just be feet, not feet cubed, because it's only height. Feet cubed is because this was volume. But we know that it's feet, and then our time is minutes. So the height's changing at 0.497 feet per minute. Now, what if we did want to worry about R? There is a different way of solving this problem. This second way of solving the problem does take R into account, and it doesn't it doesn't have a substituting, rather. So we end up keeping V in terms of both R and H, and again, we're going to run into the issue of we need dr dt. So we already have this information here. We're going to have an R and a dr dt when we find dv dt and differentiate with respect to t. We already have figured out that R over H equals 2/5, and solving for R, we got that R equaled 2/5 H. So we can find dr dt here. What we can do is differentiate both sides with respect to t. So dr dt is 2/5 times, and then using the power rule, it's just the derivative of h, which is just 1 times dh dt. So we have dr dt, it's right here, it's in terms of dh dt. Then we also need to find r. When h is 6, we can find what r is. So if we know that h is 6 at this moment we care about, and we know the relationship between them, we know that r is 2/5 times h. So we know that r equals 2/5 times 6, which is h. So it would be 12 over 5. So we would know those three things. That means that we don't have to do any substitution. So way 2 is finding dv dt, differentiating with respect to t, bring the pi over 3 out front, and then use the product rule. The product rule is u times v prime plus v times u prime. So it's r squared times the derivative of h, which would be r squared times 1 dh dt, which is just dh dt, plus h times the derivative of r squared with respect to t, which would be 2r dr dt. In doing this, we can replace everything with what we know and substitute in. So we have every h will be 6, every r is 12/5, and dr dt would be 2/5 dh dt. Now, I just plugged everything in. We know that dv dt is 9. We were told that from the start. We have the pi over 3. I replaced r with what it equals, 12/5. It gets squared. dh dt is what we're solving for. H is 6. 2 times r is 2 times 12/5, and dr dt is 2/5 dh dt. This is a lot. This way is probably a little more difficult, but I just wanted to show both ways. So we'll have pi over 3. Then on the inside, we'll have 144 over 25, and we'll keep going here. And we get the following here when we clean up. Next, I'm going to get rid of the pi over 3 outside by multiplying both sides by 3 over pi. When we do that, we'll get 27 over pi on the left-hand side. On the right-hand side, we can combine like terms here because they both have 25 as a denominator. So 144 plus 288 is 432. So we'll have 432 over 25 and then dh dt. From here, we can multiply both sides by the reciprocal to get rid of it. So we'll multiply both sides by 25 over 432. Then when we do this, 432 is divisible by 27. And we're left with our final answer, which we got in way 1, which we should have, which is 25 over 16 pi, which as we saw before was about 0.497, which is still left here from before. So it was 0.497 feet per minute, and that is the rate of change of our height with respect to time when the water is 6 feet deep. We'll end on this screen once more. Really, the most important thing is that you know what you're asked to find and that you draw it out. When in doubt, draw it out. Another important thing is understanding the difference between something that is a constant, that never changes, and something that we're given as a number, but is just a number at that instant. So we have to keep it as a variable until after we've differentiated. All right, I hope you've learned a lot about related rates. I think these problems are really fun. They're similar to optimization in that they both use differentiation in order to solve basically an applied word problem, and they're similar in a sense that we do need to draw things out. Related rates problems and optimization problems are different in that optimization is asked to maximize or minimize something, whereas related rates is more exploring the relationships between the different variables that change with respect to time.